Hey folks, my name is Nathan Johnson and welcome to lecture 7 of Advanced Linear Algebra, which is all about the dimension of a vector space. Okay, so the starting point for this lecture is to remember that every vector space that we've seen so far has lots of different bases. Like we've seen standard bases for all of these vector spaces, like the vector space Fn of tuples of n numbers from the field F, the vector space of polynomials. We've seen the standard basis just of monomials in that space. The vector space of matrices, standard basis in that case, just every matrix in the basis has a 1 in one entry and zeros everywhere else. So we've seen those standard bases, but we've also seen other bases for some of those vector spaces as well. And all of those vector spaces and vector spaces in general have multiple different bases, and they can look very different from each other. Okay, but there's one important property of bases that does not change from one basis of a vector space to another, and that is how many vectors are in the basis. Okay, so in other words, if I give you a vector space and you construct for me some basis that consists of 7 vectors for that vector space, well then every other basis for that vector space is also going to have exactly 7 vectors in it. Even though those 7 vectors might look very different, the number of them is never going to change. Okay, so that's sort of our first goal for today's lecture, is pinning down that result, seeing where it comes from. And well, we're going to use coordinate vectors to help us show it. Okay, so here's the setup. Here's sort of the main theorem for this lecture, is this guy here, and this is going to give us what we want. Okay, so suppose you've got any old vector space and you've got some basis that has n vectors in it. Okay, so a basis of size n. Okay, then the theorem tells us 2 things. It tells us that if you have any set of vectors that has more than n vectors in V, well then that set is necessarily linearly dependent. Okay, so any set that is larger than a basis of the vector space is necessarily linearly dependent. And then sort of on the flip side, if you have any set that is smaller than a basis, so a set with fewer than n vectors, then it necessarily cannot span the vector space. Okay, it's not big enough to span the vector space. Okay, and again, if you think back to sort of just vector spaces like Rn, where maybe you're a bit more comfortable, this is hopefully sort of intuitive. Imagine that you have a plane, right? Okay, and you construct a basis of that plane consisting of 2 vectors that are pointing in different directions. Okay, then the first part of this theorem says, well, if you take any set living in that plane that contains 3 or more vectors, it's going to contain redundancies. It's going to be linearly dependent. Okay, you're going to be able to construct at least one of those 3 vectors out of as a linear combination of the other 2, and that makes sense, right? If you have 3 vectors on a plane, there's some redundancy there, right? Like the third vector doesn't really give you a new direction. And part B here, I mean, if I have a set with fewer than 2 vectors, right? So I have just 1 vector on a plane, well, that's not enough to span the whole plane, right? It's just not a big enough set to span the vector space, right? So that's the idea here. And the way that we're going to prove it is we're going to use coordinate vectors, okay? So remember, this was the subject of the last lecture. All right, so we're going to start off, we're going to prove property A here. We're going to prove the linear dependence property when you have a set that's larger than a basis. All right, so what we're going to do, if we want to prove linear dependence, then we set up this linear independence equation here, and we want to show that there's some non-zero solution of it. In other words, start off, suppose that there are m vectors, and m is bigger than the number of vectors in the basis. Okay? And we want to show that this linear dependence relationship here, we want to show that it has a non-zero solution. We want to show that there's a solution here that has at least one of those scalars, c1 up to cm, not equal to 0. That's how you show linear dependence. All right, well, what we can do is we can just take coordinate vectors on both sides of this equation here. Coordinate vectors with respect to the basis b that we've got at our disposal here. Okay, so if we take the coordinate vector of the vector on the left-hand side with respect to b, that had better equal the coordinate vector of the vector on the right-hand side with respect to b. And, I mean, this is maybe a minor theorem in itself here, but it should be reasonably believable that the coordinate vector of the 0 vector with respect to any basis is always just the 0 vector, right? This is just the vector that has n 0 entries in it. Because how do you write 0 as a linear combination of the members of b? Well, just 0 plus 0 plus 0, and so on. Okay, on the other hand, we can compute this coordinate vector on the left here in a different way, right? Remember, we talked about the fact that if you have a linear combination inside a coordinate vector, you can sort of pull that outside, right? Taking coordinate vector with respect to some basis, you can just apply that to each of the vectors individually and pull scalars and vector addition outside of the coordinate vectors. Okay, so this single coordinate vector over here is equal to this linear combination of coordinate vectors over here. Okay, and now this over here, we can write this as a matrix equation, right? Because now all of these vectors are just the type of vectors that you saw in introductory linear algebra. These are all just lists of numbers, right? So if we think of v1 with respect to b as a column vector, and then v2 with respect to b as a column vector, and all the way up to vm with respect to b as a column vector, and then stack those as columns in a matrix, what do we get? We get an n by m matrix, right? There's n different columns here, so there's m columns in the matrix, and then how many rows? Well, we're representing these vectors with respect to a basis b that has n entries, so there's n entries in each of these columns. In other words, there's n rows in that matrix. All right, and then you can just check that if you do this, right, this matrix here times this column vector here, yeah, you get exactly this linear combination up above. So it's just sort of a trick of writing a linear combination as a matrix product, okay? And we did this trick back in introductory linear algebra a bunch of times as well, okay? Okay, so this right here, this is just some block matrix multiplication, just so that we can rewrite this linear combination in a slightly different way. Okay, but now the nice thing is, what we want is we want this to equal the zero vector, right? We're asking, is there a non-zero set of c's that makes this equal the zero vector? And well, this is just a linear system, and we know all about linear systems, right? This is an n by m linear system. In other words, there are n equations and m variables. There are more variables than there are equations. Okay, and because it's a homogeneous linear system, because it equals the zero vector, we know that there is a solution, right? The all zero solution. But then because there are more variables than there are equations, it can't have a unique solution. So the only possibility left is there are infinitely many solutions, right? So not only is there a non-zero choice for C1, C2 up to Cm, but there are infinitely many different choices for C1, C2 up to Cm. Okay, so that tells us that yes, the set of vectors that we started with, it is linearly dependent, right? We can find infinitely many choices to make this linear combination equal to zero. So in particular, we can find at least one non-zero choice to make it equal to zero. So it's a linearly dependent set. Okay, so that's part A of the theorem. Part A said that, you know, if you had lots of vectors, then it's linearly dependent. Part B, if you have a small set of vectors that cannot span the vector space, well, try that on your own. Okay, the idea is very similar. Represent the vectors as coordinate vectors, and then just go through a calculation using matrices and lists of numbers, you know, vectors in the sense of the previous linear algebra course, and everything just falls out. Right? And that's the really nice thing about coordinate vectors, right? It lets us turn a calculation in an abstract vector space, which is maybe hard to work with, into just matrices and lists of numbers, which we're more comfortable with, which we learned how to work with in the previous course. Okay. And now, so this theorem, it wasn't really what we want, right? I said that this lecture, or at least the start of this lecture, was going to be about showing that every basis has the same number of vectors as each other, okay? And this theorem, I mean, sort of has pieces of that, but it isn't quite that. So the corollary that we get out of this, though, is what we want, okay? So corollary 2.3 is, yeah, if you have some vector space and some basis in that vector space consisting of exactly n vectors, then every basis of that vector space consists of exactly n vectors. So in other words, every basis of that vector space has the same size as each other, okay? And the way that this comes from the previous theorem is just ask yourself, okay, suppose that I've got some other basis C, okay? So I've got this basis B of size n, but then I've got some other basis C for the same vector space. Well, if that basis were bigger, if it had more vectors than n vectors, then it actually would be linearly dependent, so it wouldn't be a basis at all. On the other hand, if it had fewer than n vectors, then it wouldn't span the vector space. So again, it would not be a basis at all. So the only way that it actually can be a basis is if it has exactly n vectors, as if it has the same number of vectors as B. Okay, so that's how you get that every basis of a vector space, or you know, at least a vector space consisting of a finite basis, they all have to have the same size as each other. Okay, and the really nice thing about this corollary here is that it lets us define a really important quantity about vector spaces. It lets us define what we call the dimension of a vector space. Okay, so here's how it goes. Suppose that you've got some vector space V, then we say that it's finite dimensional if you can find some finite basis of that vector space, and we say that its dimension, it's exactly the number of vectors in one of those bases. Okay, and because every basis has the same number of vectors, this definition actually makes sense, right? I mean, if we didn't know that every basis had the same number of vectors, then you would say, okay, well, which one of its bases are you talking about? But now it doesn't matter. Just pick any old basis, and that basis, its size, it's the dimension of the vector space, okay? And every basis has that same size. Okay, and if the vector space, we say that the vector space is infinite dimensional if we cannot find a finite basis of it, okay? And we just write that as dim of v equals, infinity symbol. Okay, so again, if you think back to Rn and subspaces of Rn, this is hopefully sort of intuitive, right? If you have two vectors, okay, not parallel, okay, you know that that's a basis of that plane, as long as they're on the plane. Okay, and yeah, I mean, the dimension of a plane is 2, right? Because, well, there are two vectors, and again, we sort of talked about the intuition of the vectors in a basis sort of corresponding to different directions. Okay, so the dimension of a vector space is it's the number of different directions that you can go in that vector space. All right, so that's the idea here. So let's go through a couple of different vector spaces that we've seen so far, write down sort of a standard example of a basis in the vector space, and then see what that tells us about the dimension of that vector space. All right, so, I mean, most standard example of a vector space is Fn, which, I mean, it's Rn or Cn or whatever, depending on whatever field you're working with. Okay, and we've already talked about how the standard basis in this vector space consists of these standard basis vectors, right? E1 has a 1 in the first spot, E2 has a 1 in the second spot, and so on, up to En has a 1 in the last spot, the nth spot. And because there are n of these vectors, right? 1, 2, 3, just count them up. There are n of these vectors, so that's what the dimension of that vector space is. Fn is n-dimensional, which, I mean, again, hopefully that's sort of intuitive, right? Rn is an n-dimensional space. Yeah, seems right. Okay, next up, space of polynomials of degree less than or equal to p. Okay, well, again, we wrote down a standard basis for this vector space already, just the monomials, 1x, x squared, up to x to the power p. So if we want to know what the dimension of this vector space p to the pp is, well, it's just you count up the number of vectors in this basis here. Well, there's 1, 2, 3, be careful, there's p plus 1 of them. There's not p of them because there's sort of this extra 1 corresponding to x to the power 0 here. You're sort of counting starting from 0. So you get p plus 1 vectors in that basis, so it's a p plus 1 dimensional vector space. All right, the vector space of matrices. Well, the m by n matrices, again, standard basis here. Again, remember, Eij has a 1 in the ij entry and 0s everywhere else. Okay, and there are mn of these matrices because there are mn different spots where you can put that 1. Okay, so this vector space is mn dimensional. All right. Going to some slightly more exotic vector spaces. We haven't talked about this one yet. The vector space just denoted by p, that's the vector space of all polynomials where we don't care about their degree. Okay, and for this one, it's sort of not too nasty of an exercise to show that this is a basis of this vector space of all polynomials. Okay, and again, we just call it the standard basis of that vector space. Just consists of all polynomials, but don't truncate off at the pth power. Just keep on going. Okay. This set here, there are infinitely many different vectors because, I mean, you can just keep on going. There's x to the power 4, x to the power 5, and on and on and on. So this vector space, well, it turns out it's infinite dimensional, right? You've got this basis that's infinitely large, so it's infinite dimensional. There is no finite basis, because if there were a finite basis, then we know from that previous corollary that every basis would be of that same size. It would also be finite in particular. Okay, next up, this vector space f of functions, okay, so just all real valued functions, okay, we're going to talk about this a little bit more later. We haven't seen a basis of this vector space yet, and there's a very good reason for that I'll talk about down below. But I can tell you that, well, I mean, f contains p, so it should be believable that it's also infinite dimensional, okay? I mean, if the vector space of polynomials is infinite dimensional, f is somehow bigger, right? It contains p, so it better also be infinite dimensional. And similarly for C, this sort of funky curly C here is the vector space of all continuous functions, continuous real valued functions. Again, it's going to be infinite dimensional just because it contains P. But again, we haven't seen a basis of it yet, and there's a good reason for that. Okay, so let's talk about that. Okay. Bases of infinite dimensional vector spaces are really, really tricky. You have to be really careful. Okay, every finite dimensional vector space has a basis. Okay, and that's just from definition. If you go back up and look at that definition up here, a vector space is called finite dimensional if it has a finite basis. Okay, so yeah, just by definition, every finite dimensional vector space has a basis. Okay, so for example, Rn has a basis. Every subspace of Rn has a basis, right? So like planes through the origin always have a basis. You know, three-dimensional lines through the origin have a basis. Three-dimensional subspaces through the origin have a basis, and so on. Okay, but when you go to infinite dimensional vector spaces, so these funky things are a little bit harder to picture, it's a lot murkier, okay? You have to be a little bit careful. I can't even tell you whether or not every infinite dimensional vector space has a basis because it depends on something called the axiom of choice, okay? And long story short, it's independent of the other standard axioms of mathematics, okay? So in other words, you can neither prove nor can you disprove that every infinite dimensional vector space has a basis unless you use this extra axiom here, okay? It's actually equivalent to the axiom of choice. If every infinite dimensional vector space has a basis, then the axiom of choice is going to hold. And if you assume the axiom of choice, then every infinite dimensional vector space is going to have a basis. Okay, so sort of the upshot of this is that even if you accept the axiom of choice, which most mathematicians do nowadays, by the way, most mathematicians say, yeah, axiom of choice, fine and dandy, I like it. But I mean, you still can't actually write down the bases for these vector spaces, okay? And I mean, sometimes you can, like for example, in this previous example, the set of polynomials, yeah, there's a basis. Doesn't depend on the axiom of choice. It's just there it is. It works. But for f and c, for example, well, let's focus on c, the vector space of continuous functions. And let's try to think about how we could write down a basis for that vector space. Well, I mean, you could start off, just throw all of your favorite functions into a set. Throw in all of these guys so that you got the polynomials to start with. But then there are continuous functions that are not in the polynomials. So maybe throw in e to the x and then throw in ln x. Well, you have to be careful with ln x because it's got discontinuities. Maybe not that one, but 1 over 1 plus x squared. And throw in all of your other favorite continuous functions there. You're still not going to have a basis. And sort of the reason for that is there are a lot of really pathological continuous functions out there. And I've sort of got a little picture of one down here. This is a picture of something called the Weierstrass function. Okay, and to show you what's weird about that, I'm going to go to a different window here. Okay, so this is a larger plot of the Weierstrass function. And the neat thing about this function is, yeah, okay, so first off, it's continuous. So it's in that vector space of continuous functions, but it's not differentiable anywhere, okay? If you think back to sort of what differentiability tells you in terms of graphs, that means it's sort of jagged everywhere, right? Remember, you sort of had these characterizations of differentiability where it's like, okay, if it's not differentiable at a point, but it's continuous there, then you've got a corner, or maybe you've got a, you know, sort of a vertical spot, like you got a vertical tangent. Okay, so here, sort of the idea is basically you've got a corner everywhere. It's just sort of infinitely jagged. So if I zoom in on a spot, it's never going to start looking like a straight line, right? Differentiable functions, if you zoom in, eventually they start looking straight. And that just doesn't happen for the Weierstrass function. Okay, and there are infinitely many different functions like this. Like this one, I mean, it's sort of cooked up in the sense that it's hard to find the formula for it, but it's not cooked up in the sense that like they're very common. There's lots of functions like this. And to construct a basis of the vector space C, you've got to have functions like this in it. Okay, and the reason for that is if you only work with nice functions, differentiable functions, so things like polynomials, e to the x, and so on, most other named functions, and then you take linear combinations of them, because linear combinations are finite, remember, you only have finitely many terms in the sum, it's still going to be differentiable. So this guy here, there's no way to write it down as a finite linear combination of sort of nice named functions. Okay, so you need weird pathological functions in your basis. But even if I throw this in my basis, it's still not a full basis for the entire vector space of continuous functions. There's just no way to write it down. It depends on the axiom of choice, okay? And if we were able to write down explicitly, it wouldn't depend on that axiom, right? We would just be able to point at it and say, yeah, there it is. All right, so bases of infinite dimensional vector spaces, yeah, for the purposes of this course, we're going to say that they exist, but just know that it's sort of murky, and a lot of the time, you can't actually write them down. All right, so that's it for today's class. I will see you all next lecture.